Hey everybody, Mr. Lally here, your physics pal. I sure hope you're doing okay. We're going to take a deeper dive into Snell's law today. You may remember from last lecture that Snell's law is a relationship that describes a law of refraction. That is, what happens when light goes from one medium into a new medium. It's got a pretty eccentric history, as it turns out. It goes back well over a couple thousand years. And in fact, Claudius Ptolemy, famous astronomer, had a version of it. There were Persian scientists who had versions of it. Lots of Asian astronomers, Asian natural scientists did work on it. So it has been around, but the form that we learn, n1 sine theta 1 equals n2 sine theta 2, is typically called Snell's law. He actually worked it up, but he didn't publish it in his lifetime. Rather, René Descartes was familiar with his work and was one of the people to make sure that it was in fact named after him. So anyway, let's kind of dive into how this thing works. There's lots of ways to think about Snell's law. We'll look at a couple of them. So Snell's law, again, traditionally written n1 sine theta 1 equals n2 sine theta 2. N1 and N2 are things called index of refraction, or indices or indexes of refraction. And what they are is a way to quantify how dense the medium is. But it's not the kind of density that we normally think of. It's not like a mass per volume, kilograms per cubic meter kind of density. It's what's called optical density. If any of you wear glasses, and especially if any of you have particularly bad eyesight, the optician or optometrist will often try and convince you to get high index lenses. High index lenses are literally made of they're polycarbonate that have an index of refraction that is generally above 1.6. And the good thing about that is that it can refract the light a lot while not being so terribly thick. Glass has an index of refraction of about 1.5. Polycarbonate is over 1.6. And that small difference means that you can have thinner lenses and lighter materials, as it turns out. Anyway, we can talk more about that at some other point if you're interested, especially. So this again is the law of refraction. You've seen this already. N1 sine theta 1 equals N2 sine theta 2. There are other useful forms. You can look at it as a ratio. The ratio of N1 over N2 equals sine of theta 2 over sine of theta 1. You can even look at it as N1 over N2 equals sine theta 2 over sine theta 1 equals V2 over V1, which would be the speed in the new medium over the speed in the old medium. What you see there is that the ratio of indexes of refraction is inversely related to the ratio of the speeds of light in the given mediums. The day you worked out this problem, it's worth taking a look at again if you don't remember, but we're going to look at a couple of other sample problems here. So this is a classic problem where light goes from one medium, usually air, into another medium, typically more dense. Now, sample problem number 2. We have light that's coming from air, index of refraction of 1.000, and that is pretty typical for air, by the way, 1.000, and usually it starts about the 10,000th place where it starts to become different than a vacuum. Let's go from air into ice, and then from ice it goes into glass. Air's refractive index is 1. Ice has a refractive index of 1.31. Glass has a refractive index of 1.5. We're going to solve for theta 2 and theta 3, which would be that refractive angle in there and then the refractive angle down here. So follow along. This is also in the slides, of course. Back to Snell's law, n1 sine theta 1 equals n2 sine theta 2. Plugging numbers in, we got 1 for n1 times sine of 60 equals 1.310 times sine of theta 2. Next, sine of 60 times 1 is 0.866, and that equals 1.310 sine theta 2. You divide both sides by 1.310, and you get the sine of theta 2 equaling 0.66. Now, on your calculator, you really have to make sure that you're in degrees mode. If you're using Google Calculator, that's cool, but make sure that it's set up for degrees. If you're using a TI calculator, then you want to look at the second big button up at the top, the one that says mode. You click that, and you're going to see some options like, do you want normal or scientific notation? And then the third option down is radians or degrees mode. For Snell's law, you absolutely want to be in degrees mode. So you got sine of theta 2. What do? Well, that's the sine of the angle. How do you get the angle from that? You got to do the inverse sine. which some people call arc sine or sine minus 1 of 0.66, and that gives you 41 degrees. The way you do that on the calculator is you hit second sine. Second is what looks like an orange key to my semi-colorblind eyes. Second sine, if you look above sine, it'll give you sine minus 1. So second sine of 0.66 equals 41 degrees. Okay, that's theta 2. We got a little bit of fortuitous geometry here. These surfaces are parallel, so these are parallel normal lines cut by a transversal. That means theta 2 there equals theta 2 here. So you're now going from ice into glass. Here's your new first initial angle, so you could call that theta 1 if you want. I'm not going to get that crazy about it, but anyway, the this will be your new theta 1, I guess. I know it seems really confusing. Theta 1 and N1 only refer to the initial medium. So if you solve this for theta 3, which is the angle down here, boy, oh boy, I can really now see why people start to hate physics with all the different symbols. It does get very confusing. You end up getting 35 degrees. Now, I didn't work that out for you, but I'll just kind of walk you through it right here. You have N, which is 1.310 times the sine of theta 2, which was 41 degrees, and that equals 1.5 times the sine of theta 3. And once you go through the calculator work, you should end up with a theta 3 of 35 degrees. Let's take a look at another example. Sample 3. So light's going to go from air into salt water of an unknown index. And in this case, we're going to use Snell's law to figure out what the index of refraction is. This one looks trickier because I've given you more info than you actually need. But in any case, initial angle is going to be 40 degrees. Angle inside the salt water is 28 degrees. So that's 48 degrees. I'm sorry, 40 degrees here, 28 degrees there. What's the index of refraction of this particular solution of salt water? As you chemistry buffs know, you can make salt water of a whole lot of different, an infinite number of possible densities as you want. But for this particular one, we're going to say it's 20%. Set up your Snell's law, and 1 sine theta 1 equals n2 sine theta 2. 1 sine 40 equals n2 sine 28. Sine of 40 is 0.64. You'll divide by sine of 28, which is 0.47, and you end up with n2. This one's actually easier because you don't have to do any inverse sine business. So you end up with an index of refraction of 1.36. It's worth pointing out here again that the index of refraction has no units. Okay, now we're going to take a look at this thing called total internal reflection. I briefly touched on it last week. This is what happens when light goes from a more dense medium to a less dense medium. Imagine being underwater and shining a flashlight or a laser. So it's basically going to come out, it's going to move away from the normal line. Instead of continuing straight, it would go away from the normal line, but there is an angle so great inside the water, we call the critical angle, where the light just skates across the top, and any effort, any angle greater than that critical angle will cause the light to be reflected back inside. So we're going to calculate an expression for this, the critical angle. So how do we find out how this is? What we do is that we, of course, use Snell's law. Now, this gets a little strange because N1 would be the index of the material inside, or where the light starts out. Theta 1 is the critical angle. N2 is going to be the index of refraction outside, which is going to be presumably air. And sine of theta 2 is going to be 90, sine of 90 degrees, because that is, if we go back one slide or two, that is the refracted angle right here. So we're looking for the minimum angle to cause an exit angle of 90 degrees. So we got N1 times the sine of the critical angle equals 1 sine 90. You trig buffs know that sine of 90 is also 1. And you're left with sine of critical angle, N1 times the sine of the critical angle equals 1, or sine of critical angle equals 1 over n, or critical angle is equal to the inverse sine of 1 over n. This is how we calculate the critical angle of a material. And what that critical angle actually represents is the angle at which inside a dense medium light cannot leave. There's a whole lot of ways to show you this. Let me show you a couple right here. So I haven't demonstrated this. I should do this. I should do this when I return, but this is what you're actually seeing in the images here. You are seeing some plexiglass is kind of bent, and then on one side a laser is being is being shot from over here. And you can see it looks like it goes around and around and around. What you can't actually see is that it, in fact, is going it's actually bending at various angles. You'll see that better in the next image. So this exhibits total internal reflection. It looks like the whole thing is being lit up. This is where it's much easier to see. So you've got light entering here. It hits, thanks to the bend here in this pipe, this light pipe. Hits there, it bends. It actually cannot escape right here. It bends up there. Now it's starting to kind of spread out a little bit because of the plastic. It's going to dissipate just a little bit, and this image isn't the best, but bounces there, hits there, comes down there. This is an example of what we call total internal reflection. It's also how fiber optics work. There's a beautiful little fiber optic lamp that many of you have seen before. Some of you may have seen like holiday lights that have fiber optics in them, maybe holiday trees that have fiber optics in them. Pretty common. Let's talk just for a couple minutes about prisms, because how prism is shaped causes the light to refract. And it causes the light to refract in kind of unexpected ways if you're not used to the idea. So we have a light that comes in and it bends toward a normal line, goes this way, bends out away from a normal line, like so. Kind of hard to tell from this picture, so let's look at it in slightly greater detail. Here's the incoming ray, normal line number 1. So instead of continuing straight here, it goes across. There's a new normal line here. Normal means perpendicular. And then instead of continuing straight that way, it bends away from the normal line. Okay, so that's cool if it's a laser. Nothing strange happens with a laser. You've seen this with the laser optics lab. But if it's white light, things get much stranger. Now, Newton figured this out 300 plus years ago. If it's white light, the light actually breaks up into its constituent colors. But why is that? Well, here's something that's kind of strange. The index of refraction is, again, a way of expressing how optically dense something is, a medium is. The actual optical density of a medium, other than in a vacuum, depends on the wavelength. There are different wavelengths that have slightly different speeds in non-vacuum mediums. So red slows down by a certain amount, but violet slows down by a slightly lower amount. And that means that red light goes through a material like glass a bit faster than violet light. Red comes through first. And you end up getting something kind of like this. Now, this is just showing you what looks like 6 or 7 different colors: red, orange, yellow, green, blue, I guess indigo, violet. But that's exactly what's going on. The red experiences a slightly different index of refraction than the violet does. But it's enough, thanks to the weird geometry of the prism, it's enough so that the actual spread becomes pretty pronounced. That's what it looks like if you imagine light being waves. Here's what it looks like if you imagine light being particles or corpuscles. Either way the theory works. Newton thought that light was made of particles. He wasn't quite right on that account. But it's also not correct to say that light is made of waves. In fact, the correct interpretation is that it has attributes of both. So again, if the light enters as a white light, it gets spread out into its colors. And what's cool about this is, depending on the kind of light that it is, it's going to have a different kind of a fingerprint, I guess is the way to put it. So typical white light is going to be Roy G. Biv. But if you have sunlight going through water droplets gives you a traditional rainbow. What you'd never notice is that there's actually some missing lines, believe it or not. Different gases have different chemical fingerprints, and this includes air, and it includes water. They have slightly different chemical fingerprints, which means we get different spectra as a result. It's actually how we identify what stars are made of. It's how we identify what the sun is made of, just by looking at its spectrum. So here are some different line spectra. This kind of, you can imagine this as being the other side of the prism. The light goes through, it bends up, and you end up getting specific lines. Right over here, Mercury's got some really weird spectral lines. Lithium has a few spectral lines like so, cadmium, strontium, calcium. Sodium, if any of you know what sodium lamps are, they're really, really, really yellow. It's got a really prominent yellow line. So this is how we can tell what stuff is made of. The whole science is known as spectroscopy. So what we're going to do as our next lessons, we're going to get into lenses and exactly how they work. I thank you for your patience and for being able to learn even though I wasn't there. We'll catch up on stuff as soon as I return. Thank you.